And thanks for being patient, because this is a continuation of my last video in which we were discussing Descartes' rule of signs as well as potential rational zeros with upper and lower bounds, concerning those things, okay? So I say thanks for being patient because I realize, I generate examples when I go through these problems, and typically examples that work out nicely with what I'm trying to show. And I realized in the last video I had actually called this last term minus 15 for lack of better eyesight, I did so. But let's go ahead and take a look at this example, and thank you again for being patient. So we say, all right, so given a polynomial, we want to be able to solve this, find some potential zeros for it. So we say set the whole thing equal to 0. Let's solve for some x values. So now tying everything together, okay, that is, our fundamental theorem of algebra and the potential rational real zeros and upper lower bounds and Descartes' rule of signs. We're going to put all that together to help us find the zeros of this, starting with the rational roots test. Okay, so let's go ahead and generate our list of potential rational roots, which are of the form p over q. P being the factors of the constant term here, -5. So we say those factors are plus or minus 1 and plus or minus 5. Okay, and we say the factors of 9 are plus or minus 1, plus or minus 3, and plus or minus 9. So given this list now, what I'd like to do is kind of try to narrow it down if at all possible. And the first way we'll try to narrow that down is use Descartes' rule of signs. Okay. Now Descartes' rule of signs concerns itself, again, with sign changes in this function. So we look at this to begin with, and we say, okay, so looking at this, we say it starts positive here. We get a positive 9, and actually I'll switch over to like a yellowish color to illustrate this. We say, okay, so positive 9. Goes from positive to negative, that's one switch. From negative to positive, that's two switches. And then from positive to negative. So we say possible, positive rational zeros. We say 3, and then we also go down by even increments here. So we say 3 minus 2, or 3 minus 4, or 3 minus 6, until we get down to like 0 or 1. But we say 3, and then minus 2 be 1, and we don't want to go negative. But we say there are possibly 3 or 1 real rational zeros. And in order to test for possible negative rational zeros, what we'll do is we'll plug in a negative x wherever we see an x. In the last video, we kind of mentioned that if we plugged in a negative x for every x, as a matter of fact, why don't I just go ahead and up here kind of write that out. Negative xq, okay, so oops, minus 15 negative x squared plus 11 times negative x minus 5. Okay, we end up with negative 9x cubed, since this is an odd exponent there. It's not going to, it does change its sign. We say this one has an even exponent, and anything to an even exponent always pops out positive, so we just say that's x squared. It's be minus 11x and minus 5. And again, we just kind of said anything that has an odd exponent is going to be flipping its sign. But we say once we do that, we notice that there are no sign changes throughout the whole thing. So the good news is this has 0 possible rational real roots. So, going back to our list up here, we've just narrowed it down by half. We said, hey, none of these negative ones are going to work, okay? So now that we've got that, we said we could always start by testing out, say 1. 1's always a good one to start with. For the sake of this example, why don't we start with -1? I just want to show you guys what's going to happen when we try to select -1. So we say, all right, dropping in our array here, we'll drop in our coefficients of the original polynomial, which were 9, -15, 11, and -5 respectively. We say, okay, so what if we tried -1 to begin with? Okay, carrying down the 9, we say we're plugging in a negative potential zero here. We say, okay, so carry down the 9, this is -9, this will be -24. Negative times a negative is a positive 24. We say, okay, this becomes 35. Sorry if I'm going fast here. And then -35 and -40, and obviously this does not come out with a remainder of 0. But the point here being essentially that when we plugged in this negative number, we said, okay, so all of the signs in the last row, they were alternating, which would necessarily indicate that the -1 is a lower bound of this function. That is, okay, anything less than -1 would not work. So we say, okay, so -5 would not work. And of course, we've already indicated that none of the negatives are going to work. But I just wanted to say, okay, when we plug in a negative, it will be a lower bound for this, and that's what necessarily would occur. Okay, so let's try choosing, say, an upper bound for this. I happen to know that 5 is too large. We'll take a look at a graph of this here in a minute. But I say 5 is too large, but I want you to just recall what it would look like if we found something that would be an upper bound. So when we plug in a positive potential zero out here, just recall that, we'll carry down the 9. We say 9 times 5 is 45, plus this is 30 times 5 is 150. This becomes 161. And of course, this is going to be very large positive, and we say this is going to come out to be positive. But when you plug in a positive here, and the whole last row comes out to be positive, we can also conclude that this is an upper bound for the function. Okay. So that being the case, we would choose no zeros larger than 5 or 5 or larger. So just kind of narrowing down our list is what we're essentially trying to do. But let's go ahead and if I were doing this any other time, I would start with 1. So we say, okay, so 1 times 9 is 9, plus negative 15 is negative 6 times negative 6. Okay, here we got, okay, so 5 and 0. So what we've determined now is that necessarily that x equals 1 is a 0. We've got it, okay? So we say, all right, knowing that this is third degree, it's got to have 3 complex roots. We know that one of the roots is 1. Okay, now we can go back and continue our long division, but this is chipped down significantly, so much so that we could go ahead and put our variables back in here and just work from a quadratic standpoint. The interesting thing about this is, if we try to factor it, and I'll let you go ahead and attempt that if you want to pause the video, but this is unfactorable. So in a situation like this, what we're going to have to do is we're going to have to run our quadratic formula, or complete the square, that's fine too, but I'm going to go ahead and run the quadratic formula on this guy. So setting aside a data matrix out here, A, B, and C, we see, okay, so A is 9, B is negative 6 in this case, and 5 is our C term right there. Okay, so we say, okay, so x is equal to negative b, so we got negative 6 plus or minus radical b squared, so negative 6 squared minus 4 times a. A is 9, c is 5, and this is all over 2a, and a is 9. Okay, so simplifying a little bit here, we get 6 plus or minus the radical of 36 minus 4 times 9 is 36, and 36 times 5, I believe, is 180. 180. It's all over 18. But what you're going to notice here is that the inside of this, our discriminant, is negative. So what we know we're going to be producing are 2 imaginary or complex roots. So we say, okay, so 6 plus or minus. Now 36 minus 180 is conveniently negative 144. This is all over 18. I say conveniently because the square root of 144 is 12, and since this negative's in here, we'll call this plus or minus 12i all over 18. And so we're typically interested in writing our complex numbers in standard form, that is a plus bi form. So I'm going to rewrite this again. We say, okay, so 6/18 plus or minus 12/18 I. Of course, those can both be reduced. So we say, so 1/3 plus or minus 2/3 I. And there are other 2 roots. So hopefully that helps.